let's go ahead and look at this review sheet. So again, if you didn't grab that already, it's posted on Blackboard. And what I want to do is just go through some questions and work them out kind of longhand instead of clicking through. I feel like that's better practice sometimes. Multiple choice can lead to some bad habits if we rely on it too much. All right, so first thing we're going to do is look at random samples. And what I have are some examples of trying to find out some information and drawing the sample. So let's suppose a local newspaper wants to find out what the best restaurant in Palatine is, okay? And we have some different ways of finding a sample. And what we want to do is just say, is this a good way to find a random sample? And if it's not, what's wrong with that? Okay. And I think that maybe a good idea would be to begin with reminding ourselves what a random sample is. Okay. So to have a random sample, everyone in the population must be equally likely to be selected for the sample. Okay. It's not that everyone is selected for the sample. It's just that everyone has to have a fair shot, right? So if you have somebody that's guaranteed to be in the sample and somebody else who isn't, right, that's not a fair shot. Or if you have somebody that's guaranteed to not be in the sample, okay, again, that's not giving you a random sample, okay, it's giving you a biased sample. All right. So here's a couple methods. Asking everyone who eats in the Harper cafeteria on Wednesday, April 23rd, okay, from noon to 2. Okay. This is not a random sample. Okay. So there's two problems with it. Well, there's probably lots of problems with this, but there's two main ones that I see right off the bat. First of all, we're trying to figure out what the best restaurant is, okay? And if we go to a place where you eat food, then the people there are probably not going to be, a fair representation of the whole population. They've already chosen a place to eat, so these are people that might be more biased towards that place, okay? For whatever reason. Maybe they like the food, maybe they like the prices, maybe they like the convenience. Whatever the reasons are, going to an eating establishment and asking what your favorite eating establishment is not going to give you a good representation of everybody. Okay, so one problem. Okay, one problem is that again, people might be biased when you ask them where they want to eat if you're going to an eating establishment. The other problem, just more generally, is that some people don't eat at the Harper cafeteria, right? Especially if you're not a student, if you're not associated with the college, and they could never be included in our sample. Okay, so we're definitely not, we're excluding, in this case, probably the majority of our population from being, at all able to be picked in the sample. Okay, so. Okay. And when I say can't be picked for the sample, I'm not saying that we would get most of the population. I'm saying they don't even have a chance. Okay. Asking everyone who attends Willow Creek Church on Sunday, April 27th. So again, that's not even a Sunday. I should have updated that. That was a Sunday from a previous year. Again, this is not a random sample. And I don't have the problem here of this being an eating establishment, but I still have the problem of people who go to Willow Creek are more likely to be selected, and people who don't go to Willow Creek can't possibly be selected. Okay. All right. If we sat around and brainstormed, we could find other problems with these samples besides these. I'm not saying that these are the only things that make these a bad sample. I'm just getting, an example out here. Okay. So let's look at the next one. Putting an online survey in a newspaper's website and listing its link in the paper. Okay, so here if a restaurant wants to find out, if a newspaper wants to find out what the best restaurant is, this seems like a way that a lot of newspapers would try, okay? And here you're at least getting broader access to the population. So I would say that this is a better sample than the other two. Okay, because at least in this case, we're not completely excluding large segments of our population. Okay, the newspapers are, going to be a little bit more broadly circulated. However, as far as getting a physical paper, right, very few people do that anymore. And as far as, its online presence, some people look at their, local papers or get, news updates or whatever from that, and other people don't. So it's still not really going to reach everybody. But another problem with this is that the only people that are going to be in the sample are the people who choose to go and be in the sample. Okay. So it's not like somebody asked, hey, do you want to be in the sample, and skipped over somebody else intentionally. It's anybody who decides that they want to be can be in the sample. So here, one of our problems is the sample here is self-selected. Okay. When you have a self-selected sample, it can't be random because people who don't want to bother with a survey won't be in the sample, and people who do want to be in the survey get to be in the sample. So it's not random. It's not everyone equally likely. Your likelihood is completely based on your preference. Okay. Okay. So this one is a little bit more subtle, but it's not a random sample. Okay, so maybe I should highlight that part because it seems like I didn't write it right away. Um, okay. So out of these first three, these are not random samples. All right. Anybody have any ideas? How would you go about finding a random sample for this survey? Randomly pick people at the mall. That's getting better, right? At least then they're not self-selected. Um, and we are picking from a big group. We run into, a similar problem that we talked about in part B though, right? If there's certain people who don't go to the mall, they can't possibly be selected. And people who, really like the mall and show up there, on a regular basis are going to be more likely. So again, that's addressing some of the problems, but it's missing some also. Okay. So if I want to think about, well, how would I go about picking people um, so that everyone has a shot at being picked? Okay. One way to do that as well, if everyone in the area lives somewhere, I could randomly pick addresses. So that might be a way to do it and have access to everybody. So we could like randomly select some addresses and give those people a survey. Okay. So then again, it's not self-selected. Okay. It's not that everyone gets a survey. And you sort of have access to the whole population. Now, one of the things that we haven't really clearly defined here is who is our population. Is it people in Palatine, right? Is it people in the greater area? Okay. But whatever it is, we could take addresses from those areas and send out the surveys. Okay, so that's one way to do it, and there are others, and I'm sure some of you are thinking of others. Now, one of the things is when we get to real life, like it's very difficult to do things perfectly, right? To say everyone has exactly the same chance of being selected. And it's also really difficult to not have any issue with self-selected, because no matter what, even if you hand somebody a survey, they might choose not to fill it out, right? And you could say, well, isn't that self-selection? And that's getting into topics that we don't have time to really delve into in this class. But if you're doing a scientific study and you really want to find out about a population, there's a threshold for how much of your sample, how many of your participants can choose to say no. And if that number gets too high, then your data is no longer reliable. Okay, and there's ways to address that and to um, there's specific thresholds for it, right? And the more you have, the worse it is, right? So, all right. Well, let's keep moving. But we can talk a lot about collecting data and how to get good data. We just want to sort of give this rough idea. We want everyone in the population to be equally likely to be selected. So we don't want a self-selected sample, and we also want access to broad access to everybody. All right. Let's look at another problem. A company has adopted a new Get Fit plan for its employees. They're surprised to find that the weights of their employees were normally distributed, with a mean weight of 174 pounds and a standard deviation of 39 pounds. Okay. Find the percent of the employees that weighed more than 250 pounds. So in this question, one of the things to look at or to note was it says that the weights were normally distributed. Okay. And we had a homework, or we had a section, I think it was 3.8. So our 3.8 notes were about the normal distribution. And one of the things that we did there was using our calculator to compute these probabilities, okay, using this normal CDF thing on our calculator. So that's what we're going to do here. We're just going to practice going through some of these, finding these probabilities. All right, so find the percent of the employees that weighed more than 250 pounds. Okay, what I'm going to do is I'm looking at a normal distribution where the mean, mu, because it's the population mean, is 174 pounds. And the standard deviation right, sigma, because it's our population standard deviation, is 39 pounds. Okay, so if I want to find the percent of employees that weighed more than 250, so as a probability statement, I want to find the probability that my random variable x is more than 250. What I'm going to do is I'm going to use normal CDF, where I have a range of values that goes from 250 to infinity. Okay, or if I draw it on the line, right? I have my mean of 174, and here's 250, and I want to find the probability of this and higher. Okay, since it doesn't have an upper value, we could just use 10 to the power of 99, and that to our calculator is a good approximation of infinity. Okay, and then we have the mean, and then we have the standard deviation. Okay, now I wrote this the way that your calculator will paste it. I'll show you that in a second. but for most of you, you don't really need to worry about the order and separating into commas. We hit second and hit distributions to bring up the menu, and I want the second one, normal CDF. Don't use normal PDF for anything. It's not going to compute a probability for you. I want this normal CDF thing. And my lower value for the range of things I'm looking at is this 250. And the upper value, we're going to do 10 to the power of 99, where the mean is 174, and the standard deviation is 39. Okay, so most of your calculators will prompt you lower, upper, mean, standard deviation. Okay, the way I wrote it is what it pastes on the screen, normal CDF, and it does the lower, comma, the upper, comma, the mean, comma, the standard deviation. And if you have a TI-83, that's how you have to type it in on your screen. You bring up that normal CDF, and then you type in the numbers separated by commas. Okay, so we hit enter and compute, and it says 0.02566. Okay, or converting that to a percentage, that would be 2.566%. Okay, find the percent of employees that weighed more than 150 pounds. Okay. Here I drew a number line. It's getting kind of running out of space. I actually like to draw a normal distribution for these problems. And the reason I like to do that is because it gives me a good number sense, right? If I have my mean of 174, and we say find the probability that we have 150 or more, I can say like, oh, that's going to be the majority of the probability. I'm probably going to have a really high percentage here, right? Like maybe 80 or 90% or something like that. Okay, so find the probability that x is greater than 150. So greater than 250 was a pretty tiny percentage. Greater than 150, though, I think is going to be a very big percentage. So the only thing that changes here is that lower value. I still want to go from 150 and go up forever. And on your calculator, if you've already done one problem, it's really easy to type in for the next one because it saves the values. So I just have to change that 250 to a 150. And paste it on the screen and hit compute. And I get 0.73085. Okay, so my number sense was off by a little bit. I said 80 or 90%. This is 70.085%. Okay, so I didn't nail it, but it was still in that range of high values that I expected based on my really rough graph over here. Okay, find the percent of employees that weigh less than 200 pounds. So you're not required to, but again, I like to draw these. Okay, so here I have 200 over here, and I want less than 200. Okay, 174 is only 24 away from 150. It's 26 away from 200. So 200 is a little further away. So I think I'm going to get a little bit more percentage. Now this is going to the left instead of going to the right. Okay, but normal distributions are symmetric. So I think I'm going to get more than 73%, but not very much more. Okay, so I want the probability that my random variable is less than 200. So I'm going to type in normal CDF, where I want to go 200 is my upper value and go down forever. Okay, so weights of employees can't go below 0, but a normal distribution can. So just to make sure that we include all the probability down there, we're just going to use negative infinity. So I'm going to use negative 10 to the 99 as my lower value, and 200 is my upper value. Okay, so I'm going to type that into my calculator. Second, distributions, to bring up that normal CDF, that's number 2. And I'm going to do negative 10 to the 99 as my lower value. 200 is the upper. Mean and standard deviation already entered. So I get 0.7475. Okay, or 74.75%. And again, that's a little bit bigger than it was in Part B, like we said, but not bigger by much. So again, my number sense is telling me this is probably correct. Okay, find the percent of employees that weigh between 100 and 150 pounds. So here's 174, 100 to 150. It's going to be this range of values over here. Okay, and so my number sense is saying, oh, this is going to be a much smaller percentage again. Okay, so this should be just a little slice, maybe 10-ish%. So if I write this as a probability statement, I want my random variable x to be in between 100 and 150. So when I write my normal CDF, the lower value is 100 and the upper value is 150. Okay, so I'll make my lower value 100, the upper value 150. The mean and standard deviation have been the same for the whole problem. And here I get 0.2403. Okay, or 24.03%. All right, I guess 10, that was way too low. But again, it's this smaller value. I can see it's definitely less than half because to the left of 174 would be fully half, and this is just a chunk of that. All right, find the z-score of a person that weighs 180 pounds. So z is x minus the mean over the standard deviation. So I'm going to take this 180 and subtract the mean, 174, and divide by the standard deviation, 39. Okay. Now, you have to be careful. If I just type 180 minus 174 divided by 39, I'm going to get a wrong answer. Okay. What's happening is my calculator is doing the division first. So it's only dividing 174 by 39. Should have been 39. Instead of dividing the whole numerator by 39. So if I have this big fraction bar. If I want to divide the whole numerator, I have to put the numerator in parentheses. Okay, and then it gives me 0.1538. All right, any questions over normal distributions? Okay, then let's move on. Oh, go ahead.
Oh, sorry. My mic was being weird. For the z-score, we're just doing like 180 minus 174 divided by 39, right?
Yeah.
Okay. All right. Simple as that. Thank you.
Yep, and the order matters. So z-scores are allowed to be negative. So if it said find the z-score of a person who weighs 150 pounds, when I subtract, I'll get a negative number, so we'll get a negative z-score, which is okay. We want to always just use the same order. Positive z-score means above average, and negative z-score means below average. So negatives are okay. Okay. All right, let's look at another problem. Here's a data set. The following is a set of data for the weights in kilograms of members of an exercise group. I don't know, maybe they're in the same group of employees. We'll find out. We won't find out. Answer the following parts using this data. So there's more than one way to go about this. Sort of depends on when you want to put stuff in your calculator. Make a frequency distribution for this data using classes with a class width of 10. Okay, so it doesn't tell you where to start here. So you have some options. The way that we have done this in the homework is to use the lowest data value, and that's fine. And if you were to use your calculator, that's how it would set it up too. Because it's a class width of 10, you could also just make them start at a nice multiple of 10, right? Like start at 50, and then I could have, you know, 50s, 60s, 70s, 80s, and 90s, and that would be my classes. Okay. So there's more than one way to set this up because this problem didn't tell you where to start. Okay. So I think the easy option is to say, okay, here's my data class and my frequency. And I can just have this one go from, 50 and up, and the next one go from 60 and up, and so on. Okay. And then that makes it really easy to count them up because I can, I can run along and just count all the ones that are in the 50s, right? So I could say, okay, 1, I think I just get 1, right? For the 60s, 1, 2, 3, 4, 5, 6. For the 70s, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. For the 80s, 1, 2, 3, 4, 5, 6, 7. And for the 90s, 1, 2, 3. And everything's been crossed out, so I don't think I skipped over anything, and I didn't count anything twice. Okay, and then we'll just look at a total. Try to add these up. 10, 20, 29. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 30. Oh, didn't cross off this 90. There's an extra 90. Well, there we go. That's why I was being careful because I missed one. All right, that's why we double check. All right, so if I do this like this, I can like finish the rest of the problem just by doing things by hand, right? Make a histogram, no problem. Once you have a frequency distribution, a histogram is very easy. Okay, so here's 50, 60, 70, 80, 90, okay, and okay, so here's my frequency. Make sure I label that axis. These are going to be weight in kilograms. Okay, so the 50 to 60 bar is one height, and then I have 6, 12, and then I have 7, and then I have 4, with no gaps between the bars. Frequencies start at 0. Right. Here I didn't start my weights at 0 because but I did indicate that, okay, I know here it doesn't, it's not right against the axis, okay? So there's a little extra gap here, but I'm just kind of focusing on the actual information that we have. Okay. Now, once we get to mean, median, and mode and standard deviation, that's where we don't want to be doing things by hand anymore. Okay. So that's where I want to enter all of this into my calculator. Now, we could have started this by entering in your calculator. So what I'm going to do is I'm also going to show you maybe a second option where we make a different choice for the start of our data class. And option 2, if we pick a different start for my data class, I might get a slightly different looking histogram, but it does not change the mean, median, mode, and standard deviation. Okay. So what I'm going to do is I'm going to enter the data into my calculator. And just to make this easier to read, let me erase all of my, just clear this up so I can see my data values a little better. Okay, so to enter this in my calculator, I'm going to press the Stat button. On the Edit menu, I hit Enter. I'm going to list all of these in L1. Even though it looks like there's multiple columns on your calculator, if I have one data set, I need to put it all into one list. So it's going to be, a single column list for the whole thing. All right. So I'm just going to go, top down, but the order here doesn't matter. So I'm going 55, 92, 67, then I start at the next column, 68, 62, 83. But you could have done a row first, and again, as long as you get all of the data values in there, you'll be fine. Okay, so I have all the data values. In order to, I'm going to go backwards. I'm going to make my histogram first on my calculator and then write down the frequency distribution. And the way that I do that is I hit second and hit stat plot, go to stat plot number 1, make sure it's turned on, and then the type selected is a histogram. I put my data into list L1, so my X list is L1. My frequency I want to be 1. What that means is that I just want each data value that I entered to be in there once. Okay. And then oops. All right, so now I'm going to hit graph. I don't see anything. I hit zoom and go to number 9, zoom stat, and that'll give me my histogram. And it looks a little differently than this one. This isn't going to have classes of width 10. So what I'm going to do is I'm going to change my window setting here. And this is saying your lowest data value is 55, so we'll just start at 55. And I say, all right, I guess that's fine. But I want my class width to be 10. So that's what the X scale is. It says, okay, we can do that. Now, if it goes a little too high up here and you want to see that, we could also change our window settings so that this goes a little bit higher. Let's go up to 15. So you can see on your calculator, sometimes you have to play with it a little bit to be able to see everything nicely. But now if I hit trace, it'll tell me these are the bars, and this is how many there are. I have 3 in the first one, 9, 11, 6, and 1. Okay. All right, and it tells me what what each of these bars, what the class starts at. So it says 55 to less than 65. Since we have whole numbers, I'm just going to say 55 to 64. Okay, and so that gives me a different frequency than I had when I counted by hand because I was using a different starting point, different range of values. Okay, so here we get 3. So then we have 65 to 74, 75 to 84, 85 to 94, 95 to 104. That should give me a total of 30. So the one that starts at 65 has 9 and 11. Then 6 and then 1. Okay. Okay, so then we draw our bars in just like we did before. And drawing by hand on this little tablet gets a little messy. Okay, we get the idea. All right, what we really needed our calculator for is this next part where we calculate mean, median, mode, and standard deviation. We do not want to do this by hand for any size data set, but especially not at the 30 data points. It would be very difficult, very time consuming. So what I'm going to do, since I have this data in my calculator, I have all that data in L1, is I'm going to hit stat and go over to calculate this one variable statistic. So the first thing on there in the calculate menu. My list is L1. Leave the frequency list blank because I don't have that in this problem. Okay. And then I have to know my symbols, right? So X bar is my symbol for mean. So I get 76.83. And my units here are kilograms. So make sure I put that. Median, I'd have to scroll down to see that. It's 76. Okay. Mode, it doesn't tell me. What I would have to do if I want to do this by hand is look over and see if I can see which one is most frequently occurring. Okay. And jumping out at me, 76 I can see 5 times. I don't think anything else is going to show up 5 times. Okay. So I think that it's 76. Okay. If you wanted to cheat and have your calculator compute the mode for you, what you could do, since we were messing around with that histogram, I could mess around with it and change my class width to 1. So every single number gets its own bar. So then when I look at the histogram, oh, it didn't like that. I'll do 2, but not 1. Maybe 1 is too narrow for it. Okay, well, there goes the cheat menu, but I'll just look at it and say 76. All right, what is the shape of this data? Now, it's not perfectly symmetric, and which side it's lopsided towards depends on how I picked my starting value. But both of these have roughly that bell-shaped symmetric shape to them. Okay, so I'm going to say that this is bell-shaped. Okay, what is the... Oh, I didn't write standard deviation. Thank you. That's important because standard deviation, your calculator gives you 2 numbers. And which one you use depends on context a little bit. So this Sx is standard deviation, and the sigma x is standard deviation, and they're using a different formula. That's why they get a different number. One of them is the formula that you use when you're looking at a population, and the other one, S1, is the formula you use when you're looking at a sample. Okay. Just to be safe, typically, I think you can always assume that we're looking at a sample, that we're looking at sample data. And then this problem is kind of bad because it doesn't specify that this is definitely a sample. Okay, so it's kind of hard to see that. But we're typically always just looking at a sample, so we want to use this S value. So 9.8229 if I were to round. And the units are the same as they are in the data. It's kilograms. Okay. If I were to look at variance, the units would be kilograms squared, which is really weird, right, to think about. And I would just take this number and square it. Okay. One thing to note, especially if you haven't done the homework yet, just put this as a reminder. Variance is standard deviation squared, okay? And use all of your decimals, okay? Don't use a rounded standard deviation to compute variance, because that rounding, when you square it, it compounds the error by a lot. So if you're entering it into the online homework system, it's going to be wrong. And it can be, depending on the numbers, it can be off by quite a bit. All right. All right, so we're going to almost always use the S1 on the calculator for standard deviation. Now, what is the range of the data? Well, if I look on here, it conveniently tells me the max and the min. Range is the difference of the two. Okay, so range is going to be max minus the min. Okay, so it is a single number. And I'm going to take 97 minus 55. So I get 42, and again, this has units of kilograms. All right, the final part for this one was to check for outliers. So what I'm going to do is go to my stat plot, still on. This time I'm going to change it to a box plot. Okay, and I want to pick the first box plot that has the little dots marked, so that's for the outliers. My x-list is L1, frequency is 1. Okay, so you can hit graph, and maybe you'll see it, but we want to be careful. I want to make sure I hit zoom and do that stat zoom again, just to make sure that I'm seeing the whole thing. And here I can see I don't have any separate dots anywhere for outliers. Okay, so I know that I'm safe and that there are no outliers. Right, and we can draw our box plot. My minimum value is 55, my max is 97. Here, let me show you another way to do this. A way to think about your box plot is to think about a number line already labeled. Okay, so then I want to put 55 on here. My max value is 97. Okay, and you can actually just look at your calculator. If you hit trace, it'll show you all the important points, right? 55. The next one is at 71, 76, and 84. And I can just put a little vertical bar in front of each one. Okay, in the middle three, I enclose in a box. And then I draw a line out to my other two. And that's how you make a box plot. Okay. So the 5 vertical bars that I have drawn, right, and the 5 blue numbers that I wrote, is the 5-number summary, right? So when we talked about the 5-number summary back in, I don't remember the section now, 3.5 maybe. The 5-number summary is exactly the numbers that you put on a box plot. The box plot's just a visualization of it. All right, any questions about box plots? Okay, let's look at another example. This one is different. There's no context here, which is strange, but we're just going to do a quick computation problem. But here, our data is repeated data, right? So I'm already given a frequency distribution. I can see I have lots of 4s, lots of 5s, lots of 6s, lots of 7s, lots of 8s. Okay, so the way that I would enter this into my calculator, go to Stat, Edit. I'm going to clear out this old list. I'm going to enter my data into list L1, right? So 4, 5, 6, 7, 8. And then I'm going to enter the frequencies into L2. Okay. Right, so put data into L1 and put the frequencies into L2. All right. So then to make or to compute stuff, I go to Stat, calculate one variable statistics, and when it brings up this menu, I now do indeed have a frequency list. So I want to say L2, so I hit second 2 to get L2 to pop up there. Okay. You don't want to hit like alpha, and let me see if I can find the L. Maybe it won't even let me. Oh yeah, it will. You don't want to hit L and then the number 2. Notice that here that 1 is like a subscript and here that the 2 is full on. If I do this, it's going to just give me an error. What I want to do is hit second and hit 2 to enter this single item L2. Okay. And now when I hit calculate, it'll compute stuff for me, right? So the mean is 6.647. Okay, the median is 7. And notice that if I ignored the frequency, this isn't the results I would get, right? If I just took 4, 5, 6, 7, 8, 6 is the middle value. That would be the median, okay? But I don't have very many 5s and I have a lot of 7s, and that means the middle value, gets brought up higher. The mode is the number with the greatest frequency. There are the most 7s, so the mode is 7. Okay, it's not 97, it's not the frequency of the biggest frequency, okay? It's the data value with the biggest frequency. Okay, mid-range we can compute, but we're not going to talk about because we didn't talk about that in our section. So I got carried away with the M words here. Mean, median, mode, mid-range. And then the standard deviation. Remember, we always want the S1, 1.25. Okay. All right, create a relative frequency distribution. What I'm going to do is I'm going to build off of the frequency distribution that's already here and just put in relative frequencies. So what I'm going to do is add these up really quickly to find my total just for the frequencies. Okay, so if I take my calculator and add these up, 27 plus 4 plus 22 plus 97 plus 43, I get 193. I think that, let me check something really quick. Yeah, when we did this one variable statistics, it also told me that the n, which is the total number of things, it told me the 193 total there also. So that could also save you adding up 5 numbers if you caught that as we were writing down like the mean and standard deviation and so on. Okay, to find the relative frequency, what I'm going to do is just take each of my frequencies and convert it to a percentage of the whole. So I divide by the total, right? So for the first one, we're going to take 27 divided by 193. So I get 0.13, I'll go to 4 decimals, so 0.1399. Okay, so 27 divided by 193 gives me 0.1399 or 13.99%. Okay, now I wrote this number, it's the same number, I wrote it 3 different ways, and you don't need to do that. You kind of just pick one and go with it. So for the rest of these, I'm just going to write down the decimal frequency. Okay. Usually what we would do is either write it down as a decimal or write it as a percentage, and it really just depends on what we're going to do with it next. Okay, so we get 0.0207. Okay, 22 divided by 193. I get 0.1140 if I round. Okay, 97 divided by 193. I get 0.5026. Finally, 43 divided by 193. I get 0.2228. Okay, when I add these up, they should add up exactly to 1. And let's just check that really quickly. So I wrote down 0.1399, 0.0207, 0.1140, 0.5026, 0.2228, and they do end up adding exactly to 1. Okay, but again, if you were off by a tiny amount, if it was like 0.9999 or 1.001, okay, that's fine. If it's off by 1 decimal spot, that's just rounding error. Okay, so that's my relative frequency distribution. And now draw a histogram. Okay, I can have my calculator do it, but in this case, I think it's actually easier for me to just to draw it by hand because I already have a frequency distribution. Okay. For my frequency distribution, I'm just going to go up to 100. Okay, and that should be enough to cover all of these bars. So 4 is a bar 27 high. 5 is only 4 high. 6 is 22 high. 7 is 97 high. And 8 is 43 high. Okay. So there's my histogram. It didn't ask me, but if I were to label this, right, from my mode, right, from my tall center value, it's also the median, it stretches 3 bars to the left and 1 bar to the right. So this would be skewed left. Okay. So I'm just answering a question that wasn't asked there in the problem, but it's good to go over. All right, any questions on this one? Okay, just one problem left with a million parts. That's the way it goes in stats, right? Very few problems, very many parts. A veterinarian wanted to find out what proportion of pet owners that talk to their pets remotely went away. Randomly selected 150 pet owners and discovered that 54 of them spoke to their pet remotely. So I didn't have the check conditions on here, okay? But there are 54 that did talk to them. That's bigger than 10. That means that there's 96 of them that did not talk to their pets, and that's bigger than 10. That would be the conditions that we check, and we'll do that in another review. What we did want to do here is identify the individual population sample and so on. So an individual is a randomly selected pet owner. Okay. The population, from what I can tell here, is all pet owners. Okay. And the sample is the 150 randomly selected pet owners. Okay, what's the variable here? The variable you could think of as the piece of information, or you could think of it as the answer to the question that we're asking. We're asking, do you talk to your pet remotely? So the variable is whether or not the owner talks to their pet remotely. Okay, and since the data here, the answer, if I phrase it as a question, the answers would be yes or no. So I know that the type of variable, since it's yes, no, is qualitative. Okay. So then to compute a confidence interval, and I didn't write down the whole, panic acronym here that we did in the homework, but we'll do that with the next set of review material we look at. But what I still want to go through the same thing, right? I want to use this one prop z int to create my confidence interval. Okay, x is the number of pet owners that said yes, right? There's 54 of them. N is the sample size, there were 150 of them. It doesn't tell me what percentage a confidence interval. If it doesn't tell you, we should default to a 95% confidence interval. However, on the exam, you will definitely be, it will be very specific. It will always tell you the percentage. Okay, but 95 is kind of like a default. Okay, so I'm going to write down that confidence interval. So 0.28319 to 0.43618. Okay, that's a confidence interval, but it doesn't really help, right? Like if you just say to somebody, here's a confidence interval, 0.28319, comma 0.4, that doesn't answer any questions. So what we want to do is write down what that means in words. Okay, interpret that confidence interval. It was a 95% confidence interval, so we can say we can be 95% confident that the percentage of all pet owners. Okay, notice that when I interpret a confidence interval, I'm not talking about my sample, I'm talking about my population, right? The whole point is to use the sample to tell us about the population. So we want to talk about the population. So the percentage of all pet owners who talk to their pets is between, and I'm going to write those same two decimal numbers, I'm just going to write them as a percentage. So 28.319% and 43.618%. Talk to their pets remotely. Okay, I think that would be like closer to 100% if it was just talk to your pets at all. All right. Write the confidence interval as a point estimate and a margin of error. This is the way that we usually see confidence intervals in the media that we consume. Okay, and what I'm going to do here is more work than you need to answer the question, but I want it to make sense. So I'm going to write a number line, and I'm going to write the numbers for my confidence interval on here. Okay, so 0.28319, 0.43618. Okay, and right dead center here, halfway in between, that's what this p hat is, 0.36. Okay. And you could also average these two numbers to see the 0.36. Okay, but I know that's going to be it, right? My calculator tells me that p hat is 0.36. Okay, and that's my point estimate. Okay, and the margin of error is just the distance from your point estimate to the outside of your interval. Okay, because this is exactly halfway between these two, I know both of these sides are the same, right? But this distance is the margin of error. Okay, so if I want to compute that, I just subtract these, right? So 0.43618 minus 0.36. Okay, so I can see the margin of error is 0.07618. Right. So what I'm going to do is I'm just going to rewrite this same sentence that we have, but instead of talking about a range, an interval of values, I'm going to talk about a point estimate and a margin of error. So I'm going to say we can be 95% confident that the percentage of all pet owners who talk to their pets is 36%. Again, I'm just converting it to a percentage with a margin of error of 7.618%. Okay, so I have really the same sentence. It's all the same meaning. But instead of talking about this interval of values, I say that it is the middle value, and the margin of error is how far it can go in either direction. Okay, and this is the way that we typically consume media, except that in any sort of study or report that you'll see in like an article on your newsfeed or something like that, they'll never tell you the percent confidence. And I think that the reason for that is it'll probably confuse people that don't understand stats well enough, right? Be like, what's this percentage? What are we talking about here? And it's easy to confuse that with margin of error. They're different things. Okay, hopefully we know that now. And even margin of error is usually not mentioned in the same sentence with the 36%. They'll just say it's 36%, and then maybe as a footnote somewhere say margin of error. Okay, that's the last question on the review.